Hi everyone, and thank you for attending today's webinar, In Focus, Build Advanced Multi-Camera Products with NVIDIA Jetson. Before we begin, we wanted to cover a few housekeeping items. James, MKS, and Dilip have created a wonderful presentation for us today. This content is pre-recorded, which allows them to be online to answer questions real-time via the Q&A widget throughout the event. At the bottom of your screen are multiple application widgets. All of the widgets, as well as the slide area, are resizable and movable, so feel free to move them around to get the most out of your desktop space. If you have any questions during the webcast, please submit them through the Q&A widget. We'll try to cover as many questions as possible during the live Q&A portion, but if there's any we don't get to, we'll post them on the forum to keep the conversation going. Be sure to check out the resource list for links to the developer site, forums, wiki, and more. If you run into any technical issues during the webcast, you can find answers to some common technical issues located in the Help widget at the bottom of your screen. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier. And with that, let's get started.
Hello, everyone. Thanks for joining us today. My name is James Junn. I'm a Senior Product Manager on the Jetson team here at NVIDIA. And today we'll be continuing the Jetson webinar series with a session on building advanced camera products to work on the Jetson platform. Here is the agenda for the webinar today. I'll provide an overview of the Jetson TX2 and drill down into the imaging subsystem, and then talk about our camera partner program that we created in order to provide specialized service for camera development, along with some of the camera products that are available today that have been tested to work on the Jetson platform. I'll then hand it over to Econ Systems, who is our newest camera partner, to discuss how they solve synchronizing multiple cameras on the Jetson platform, and then we'll wrap it up with a Q&A session. Jetson TX2 is an AI supercomputer on a module. It has more performance for AI than a pair of Intel Core i7 desktop computers, all in a power envelope of less than 10 watts. It packs the level of computation and efficiency to deploy advanced AI to edge devices. Video from cameras is one of the largest generators of data, and the opportunity for leveraging deep learning to gain insight from that data is massive. The Jetson platform offers the right combination of performance, flexibility, and power consumption to ingest large amounts of data at the edge for real-time processing. Some of you may have developed with Jetson TX1 in the past, and earlier this year we released the Jetson TX2, which brought a considerable improvement in performance due to the newer GPU architecture, memory enhancements, additional CPU cores, and overall throughput increases, while still maintaining compatibility physically and through software for a seamless upgrade path from Jetson TX1. On the camera and video side, we doubled the video encode performance and increased the throughput for each CSI2 lane. Now we'll take a closer look at the Jetson TX2 imaging system. For video input, it has a total of 12 MIPI CSI2 lanes that are each capable of 2.5 gigabits per second. And that's split into 3 CSI bricks that allows for flexibility in how you hook up the cameras based on bandwidth requirements. For image processing, Jetson has an advanced hardware-accelerated ISP that can process up to 1.4 gigapixels per second, which is roughly 6 simultaneous streams of 4K resolution at 30 frames per second. In addition to the CSI lanes, Jetson TX2 has USB 3 and gigabit Ethernet ports for connecting your processed video cameras. Choosing the right camera interface is an important decision in determining the correct camera to meet your product requirements. As I mentioned, the Jetson platform has support for all of the listed interfaces, and there are distinct differences in the characteristics of each medium. For high bandwidth cameras that are transferring raw Bayer data, MIPI CSI2 offers very high throughput over multiple lanes, and is the most common standardized interface for interfacing directly with the image sensor. With its prevalence in the mobile space and the protocol being driven by the MIPI Alliance, there is strong adoption in the camera industry. Utilizing this interface does require some hardware expertise and the correct driver for the image sensor. Another limitation to using CSI2 is the relatively short cable lengths that can be supported. A common practice is to use a SerDes interface to transmit the video over longer cable lengths. The latest SerDes products can support distances of up to 15 meters with little to no degradation of the video fidelity. The bandwidth is also continually increasing to support higher resolutions and frame rates. USB cameras have the advantage of large adoption from the consumer market and ubiquitous availability. With its high bandwidth, ease of use, and low cost, USB cameras are ideal for a wide variety of applications. And now with the USB 3 Vision standard being created, there is a robust framework for compatibility across GigE Vision cameras as well. Speaking of GigE Vision cameras, for transmitting video over much longer distances, GigE Vision cameras can support up to 100 meters without the use of active repeaters. These cameras can also scale easily with the use of Ethernet switches and low-cost cabling. I've also listed some typical bandwidth requirements for a 1080p resolution camera at 60 frames per second, as well as a 4K resolution camera at 60 frames per second. You can see where some of the interfaces are limited for transmitting raw video versus processed YUV video. Each interface has its own unique strengths that make it more effective and efficient for certain kinds of applications. Hopefully, this helps you to better understand the differences. NVIDIA has invested resources into building relationships and training preferred partners that have specialized expertise in developing camera solutions. These partners have been selected based on their capabilities and experience in working with a broad portfolio of image sensors from the various vendors and with the Jetson platform. Some of the services they offer include writing drivers for image sensors, conducting characterization on the image quality, as well as custom tuning the image. They have been given a set of tools that grant access to the ISP parameters for tuning things like auto exposure, auto white balance, tone curve, and high dynamic range. Getting the cameras to produce specific images is paramount for both deep learning and human viewing applications. In addition to development services, they will also be able to design and build custom hardware camera modules for going into mass production. Leveraging the preferred camera partners will help accelerate your product development and help solve complex camera-related issues. Here's our current list of preferred camera partners. We have detailed descriptions for each partner and links to their website on the NVIDIA developer webpage listed on the slide. Leopard Imaging was the first to join the program in the summer of last year, and they have offices located in California and China. AppPro joined the program earlier this year, and they have offices located in Taiwan. And Econ Systems is our latest to join earlier this summer, and they have offices located in India. You can see that there is broad product availability in their portfolios, and they have experience with many of the key image sensor suppliers. Here's a list of the specific cameras that our partners have designed to work with the Jetson platform. These are raw CSI2 cameras that come with a working driver and ISP tuning files for the Jetson TX1 and TX2. They range in resolution from 2 megapixels, which is 1080p, to 8 megapixels at 4K resolution, all the way up to 13 megapixels. Some of our partners have built multi-camera solutions that take advantage of the Jetson's camera input capabilities. Specifically, Econ will talk about their 6-camera system later in this webinar. On the industrial side, we have several partners that have ported their camera SDKs onto the Jetson platform. These cameras are good for applications such as automated optical inspection, broadcast in VR, sports automation and motion tracking, and large volume 3D scanning. They tend to utilize global shutter sensors for capturing very fast motion without distortion, as seen in some rolling shutter sensors. They're also capable of very high frame rates to reduce cycle times and low latency image transfers. By using USB 3 or GigE interfaces, they offer longer maximum cable lengths, which simplify the design of large multi-camera systems. And finally, there are a number of stereo cameras that have out-of-the-box support for Jetson to help capture depth information. So today I've highlighted just a handful of the various camera products that work with Jetson, as there are many more out there. We continue to enable more partners in building camera products to be part of the Jetson ecosystem. And now I'll turn it over to our latest camera partner, Econ Systems, to discuss their 6-camera solution for Jetson and how they were able to synchronize the frames across all of the cameras.
Thanks, James. I'm happy to welcome you all once again to Econ's webinar on synchronization in multi-cameras on NVIDIA Jetson TX1 and TX2. I am MKS. I manage the ISP team in Camera Products Division of Econ. Today, in this presentation, we will cover the following. There will be a brief overview of Econ Systems. Then my colleague Dilip will walk you through the next few topics. There will be a demo of capabilities of Econ's 6-camera solution HexCam. And then we will go into the theory of synchronization in multi-camera systems and how it can be implemented. We will dwell at the hardware capabilities of NVIDIA TX1 TX2 and see how suitable the platform is for a complex system like a HexCam. We will also talk about Econ's multi-cameras for NVIDIA, how it has been done, and we will walk through a use case of such a synchronized multi-camera system. Finally, we will have a Q&A session. Econ Systems is a one-stop solution for all your imaging needs. We have been in this field for long 14 years. We offer high-speed USB cameras and board-level cameras, essentially MIPI and parallel cameras, right from 1 megapixel up to 21 megapixels. Cameras with global shutter or rolling shutter, infrared cameras, stereo vision cameras, GMSL cameras for supporting longer range up to 15 meters. We have off-the-shelf cameras that can be purchased from our online store, or we can deliver custom design cameras for specific needs. Additionally, we also have mass volume production capabilities. In short, for any of your imaging needs, call us. I'll hand over this presentation to Dilip to continue.
Thanks, MKS. Hello and welcome everyone. My name is Dilip Kumar and I'm a camera specialist at Econ Systems. Today I'll be talking about the NVIDIA Jetson TX1 and TX2 with its support for multiple cameras. We have also utilized this feature of the NVIDIA Jetson platform to implement a 6-camera solution with support for synchronization between the different cameras. I'll be explaining in detail about the synchronization feature as well as this product in detail. This video shows the 6 camera solution from Econ as well as its synchronization support. And in this video you can see that the 6 cameras are streaming 1080p at the same time, and they are all pointing towards the iPad, which is running a millisecond timer. So when the application is triggered for image capture, you can see that all the 6 cameras are paused at exactly the same time, which shows the synchronization between them. So I'll be explaining about this synchronization feature in detail in the forthcoming slides. What exactly is this synchronization feature that we are talking about? To explain this in the most simplest manner, it is the ability to capture multiple images from different cameras at the same instant of time. Normally, different cameras, when connected to the same host, do not have this capability to output images in a synchronized manner. But when these cameras are connected in such a way that they can be triggered or made to output images at the same time, this way we can achieve the synchronization between them. So the different types of synchronization used in the imaging industry are real-time synchronization and post-process synchronization. In the case of real-time synchronization, the images are output by the cameras itself in a synchronized manner, so they can be directly used in the application, and there is no additional processing of the images involved. So this is the fastest method for achieving synchronized images. And the other type is the post-process synchronization, where any normal camera can be used to acquire images and store them to the storage medium. These images should also contain additional input parameters such as timestamps, so that these images can be retrieved later from the storage to an application, and using these timestamps, these images are synchronized, and then they are used in an application. This, as you can see, involves additional processing capabilities, so it is not used in scenarios where time is of high importance. For example, real-time synchronization is used in cases where decisions have to be taken in real time, such as for automated quality inspection in the assembly line of a production plant, where the different products that are produced at high speed have to be inspected and certified. In the case of post-process synchronization, it is used for 3D reconstruction from different images taken from different cameras pointing at the same scene. So some of the techniques that are used for synchronization are hardware level synchronization and software level synchronization. So in the case of hardware level synchronization, the actual image output is from the sensor. So the best way of achieving synchronization is directly at the sensor itself. And the other type is the ISP based synchronization. So these two are part of the hardware level synchronization because these involves triggering the either the sensor or the ISP for image capture. The other method of software synchronization is based on timestamps, where the images as well as timestamps from the different cameras are used for processing and acquiring synchronization between them. This is how the sensor level of synchronization actually works. As you all know, the sensor is capable of outputting images in a specific manner. But some sensors have the additional capability of giving out images whenever it is triggered for image capture. For example, it can be an input signal to specify what is the exposure time that has to be programmed in the sensor. So these kind of features are implemented in sensors that are meant to be used in machine vision cameras. And using this signal, the images from the sensors are synchronized directly at the source, and so this This method has the highest level of accuracy without any chances of error from the imaging sensor itself. The second method of hardware level synchronization is the ISP based synchronization, where the ISP controls the sensor and the ISP outputs images to the host processor after processing the bare raw image from the different sensors. And in this case, the input trigger signal is given to the ISP instead of the sensor directly. So the ISP takes care of the different parameters of the sensor, such as the integration, blanking, and readout timing, so that all the different sensors output images in a synchronized manner. This is very useful in cases where the raw bare data cannot be used directly in the application, so that an ISP is required for applying additional operations on the raw image. And but this is also there is also a chance for images being skipped because of lack of synchronization in some cases. We'll see about this in the later slides. In the software-based synchronization, any camera that can output images as well as additional parameters such as timestamps can be used to achieve sync. So in this case, there is no hardware dependency at all involved. So it is entirely up to the application to verify the timestamp and make sure that the frames are in sync from the different cameras. For example, in the case of V4L2 camera, the V4L2 buffer actually contains the image data as well as the timestamp. So the application can process this timestamp to make sure that the images are in synchronized manner. The level of accuracy that can be achieved in this method is actually lower compared to the hardware level sync, because some cameras might output images without any lag, but some cameras might have some lag or delay in the for receiving the frames. So in such cases, this method becomes highly unreliable. This is a comparison between the different methods used for synchronizing multiple cameras, and the sensor based synchronization has the highest level of accuracy in the order of nanoseconds, whereas the ISP based synchronization we can get up to microsecond level accuracy. As for software based synchronization, we can get millisecond level of accuracy. The reason why we can get a nanosecond level of synchronization in the sensor is because the images are triggered directly at the source for image capture, and this reduces any lag in the image capture. And for sensor or ISP based synchronization, the different circuits or timing circuits are required in the hardware, so the number of components involved is higher, and so is the cost. But for software based synchronization, there is no hardware requirement at all. In the case of sensor or ISP based synchronization, the different sensors or ISP have to be programmed and configured in such a way that the synchronization feature is enabled in them. But for software based synchronization, the application has to process all the timestamps from different cameras constantly, so there is an additional overhead that is applied on the host processor. As far as error rate is concerned, the sensor based synchronization, there is no chance for any error, because the sensor is always capable of outputting images according to the input signal. But for ISP based synchronization, there is a slightly low possibility of getting some unsynchronized frames, because the ISP can discard frames whenever it detects that the sensor has not given images as per its requirement. In the case of software based synchronization, it is highly unpredictable, and depending upon the method used, the images can be out of sync for once in a 30 minutes time. So this is highly unreliable, when no other hardware-based synchronization method is used for additional redundancy. And for the type of errors that can occur, the sensor has no errors, but for ISP we can get skipped frames because of the internal logic. And for software-based synchronization, if the images are not constantly synchronized or the timestamps are not constantly compared, then the images can be get drifted because of lag in the cameras, and in that cases the images can be skipped or dropped as well. Although synchronization is a good feature to have, it has its disadvantages as well. So it is always best to use synchronization only when it is absolutely required. For example, when synchronization is implemented in the hardware itself, this increases the cost of the hardware setup, and normally auto exposure in a camera is implemented by either by varying the integration time or by varying the shutter speed of the camera. But in the case of a synchronized camera, the integration time as well as the frame rate of the camera are fixed to a specific amount. So the auto exposure is only possible by varying the shutter speed of the camera. So because of this, the output image might have a higher noise level at low light conditions, because increasing the shutter speed increases the noise as well. And whenever the synchronization has some fault, the frames can get discarded, and in a real-time scenario this is not an ideal feature, because all the frames might be required to process the images and take some real-time decisions as well. We saw in detail about the different synchronization methods for multiple cameras in the previous slides, and now we'll see about the advantages of using the NVIDIA Jetson TX2 for a multi-camera system. The main feature of the TX2 is the Pascal GPU with up to 256 CUDA cores, so which enables an AI application or a deep learning application to be run on this processor with high processing capability. And it also has support for up to 6 cameras in different MIPI combination, so that we can get a throughput of up to 41 Gbps in the MIPI part, and the ISP in the TX2 can also process up to 1.4 gigapixels per second. And this combination of hardware is ideal for designing a high-end video analytics or smart surveillance systems. This is Econ's multi-camera solution for the TX1 and TX2 called the ECAM30 Hex CU-TX2, and it has support for up to 6 cameras and can stream 1080p at 30 fps with very low CPU overhead. It uses the AR0330 sensor from onsemi, which is very popular for its low light imaging capabilities, and it also uses the Econ ISP for controlling different sensor parameters and getting the highest quality of image. We are in talks with NVIDIA to get the TX2 ISP to work with this sensor in the future, and this might be done at a later date. One of the additional features of this product is the synchronization capabilities, and we have achieved 2 levels of synchronization in this product, which is the first level is the ISP based synchronization, and later part is done in the application using the timestamps. We verify the timestamps from the different cameras and make sure that the synchronization is always running and working fine between the different cameras. This camera also produces 30 fps of image data constantly, and the level of synchronization in this product is in the microsecond level, which is a millionth of a second. Now we'll show a video of how the application can be used to control this camera. This is a 6 camera setup that we have connected to the Jetson TX2, and we have two different applications that can be used to control and configure the different cameras. The first application that you see is the HexCam, which is a command line application, and this application is used to stream all the 6 cameras simultaneously. The 6 cameras are positioned in such a way that they cover a 360-degree view around it, and this is what you see in the preview as well. The second application that you see is the eCam GUCU application, which is a GUI based application, and it can be used to control each of the individual cameras separately. This application also exposes some of the various features that the TX1 ISP has, and these can all be controlled using a simple GUI. You can see that the various parameters of the ISP, such as the brightness, contrast, gamma controls, the white balance controls and sharpness, etc., are exposed in this GUI, and they can be easily changed by adjusting the sliders near it. This is a use case where the 360-degree 6 camera setup can be used to capture a panoramic view around it and rendered on an application using stitching algorithms. This is the hardware flow of data from the cameras to the end user, and as you can see, the 6 cameras are connected to the different CSI blocks in the TX2 processor. There are 3 CSI blocks in the TX2, and each of this individual block can be configured as either a 4-lane block or 2 separate 2-lane block. So what we have done is we have configured the CSI blocks to be used in 2-lane mode, so that it can support a more number of cameras, which is up to 6, and these 6 cameras transmit the CSI data to the video input block inside the TX2 processor, and this video input block actually acts as a bridge between the internal hardware and the application. So the data is transferred from the video input to the application by the memory interface. We have also used a synchronization controller in the hardware so that all the 6 cameras can output images in a synchronized fashion. This block diagram shows the flow of data from the camera to the end application, and these cameras, being v4L2 compliant, can be accessed by any v4L2 standard application. For example, OpenCV or ROS has been tested, and GStreamer also works fine with this camera. We also have a separate HexCam application which can be used to preview all the 6 cameras at the same time, and we have implemented the control for the synchronization between the cameras as a separate v4L2 custom control, so that using v4L2 custom control APIs, the synchronization mechanism of the cameras can also be controlled. We also provide the sensor driver for this camera, so that the v4L2 APIs can talk to this driver and program the cameras using the I2C protocol. And upon receiving these commands to the I2C, this camera will be transmitting data via MIPI to the platform driver, which will translate the data to v4L2 buffer and hand it over to the application. This is a code snippet of how we have exposed the synchronization controller in the hardware to the application using the v4L2 CID frame sync command. The application can talk to the actual hardware to enable or disable the synchronization mechanism by passing a value of 1 or 0 respectively. We have also run some test cases using the eCam30 HexCU TX2, and we noted down the CPU as well as GPU usage of the TX2 processor when recording 1080p 30 H.264 or H.265 streams. So when 6 cameras were used to stream 1080p and recording was done using the H.264 codec, we noticed that the CPU usage was around 20%, but the GPU was always at 0%. So any deep learning or AI application can be run in parallel along with the encoding and streaming process. So this concludes the technical part of the presentation, and MKS will take over, and he'll be explaining about some of the use cases where the product was used for a customer's requirement.
We will now walk you through a use case for a synchronized multi-camera system, which is a smart parking guidance and surveillance. This is a system that is used for fairly big parking lots where a lot of the functionalities have to be automated. Things like automated control of the entry and exit booms. Whenever a vehicle reaches the entry point, automatically identify a free parking slot and guide the vehicle real time to the parking lot. Later, when the user comes back to pick up the vehicle, parked vehicle, guide the user to the parked vehicle. Other things like security, so on and so forth. All of this have to be automated. There are very unique challenges and enhancements we encountered when we helped our customer implement this solution. Some of them are listed here, and we will walk through them briefly. One of the challenges was extremely bright light. This can happen if it's an open parking lot and there is a bright sunlight, or if while a vehicle comes in, when the headlight directly falls on the camera. So for which we had to support automatic dynamic luminance detection and gain control. The other challenge is the other extreme of low light. We had supplemented visual data with IR data, used it to identify vehicles at low light, and to selectively disable IR filter, we had used a IR shutter. Another challenge or request enhancement we got was to automatically inspect damages of the vehicles when it has parked. This is more relevant to cases of premium parking where typically costly cars are parked, and if there are damages, it has to be detected as early as possible. Long-term parking. So for which we used to have a picture of the vehicle taken, 360-degree picture of the vehicle taken while entering and exiting, and by comparing, one can find out whether there has been any damage. So this feature especially is extremely image processing intensive. It requires quite a good amount of guzzling power, and we come to the next challenge of high computational power requirements, and NVIDIA Jetson TX2 is extremely highly suited for such a solution, having a ARM Cortex A57 quad-core CPU running at 2 GHz and 256 core Pascal GPU at 1300 MHz. Continuing with the challenges and enhancements, another important requirement was ability to locate the camera remotely a little distant away from the host processor. So this was achieved using GMSL. The distance could be up to 15 meters. A couple of other things were power saving. Of course, in a parking lot, power is not such a big priority. However, it's always welcome. Lower the power usage, lesser your bills, energy bills. So there were things like the camera switching on based on motion detection were used. Jetson itself is highly power sensitive. It has a lot of power efficiency built in. We also use things like liquid lens could be employed to reduce the powers further. Another thing was depth and distance calculation. This was can be achieved if we have multiple cameras covering the field of interest, more than one camera covering the field of interest. By collecting the field of interest from multiple cameras, one can calculate depth and distance. And this is also fairly compute intensive, and Jetson power of computation helps. Another is ability to capture images in contrasting lighting, the same field of interest having lights of different intensity. So for which, if the sensor supports HDR, WDR, we can use it. One big advantage with the solution is that these multiple cameras, some of the parameters like gain and zoom can be independently controlled, and by selectively applying the right gain, one can achieve the same. Haven't gone through an application for synchronized multi-camera solution, smart parking surveillance and guidance. We will briefly walk through some other applications for which the same solution was considered. Multi-view sports coverage is one of them. Sports like tandem sky jumping, F1 racing, so on and so forth, have immense relevance, where the same sports can be covered from multiple angles. 3D medical scanning is another important application. Any organ or part of the body that is being examined or is going to undergo surgery, ability to recreate it, 3D image helps. Warehouse robots, in which machine vision is involved, where automatically goods can be moved around, something where there is relevance for a synchronized multi-camera solution. Augmented vision, personalized electric vehicles, or a couple of other applications. In this slide, we'll talk about some of Econ's current and future products, very exciting products we are working on. Multi-camera solutions that support sensors from different vendors is one. Right now we have a sensor from a specific vendor incorporated in our multi-camera solution, but we have the ability to support sensor from any of the leading vendors. GMSL is another of the projects we are working on, very exciting, and we had mentioned it earlier in the presentation. Whenever the camera has to be located a little distant away from the host, up to 15 meters, GMSL can be employed. Stereo cameras are something that are already available. Thara HDR cameras have the ability, leveraging on the sensor, we have added our value in providing HDR capabilities, and these are also available. We would like to highlight one of the products Econ is working, in which we are working very closely with NVIDIA, the IMX290 and TX2 ISP solution. IMX290 is a sensor from Sony, 2 megapixel sensor, belonging to the StarVis family, having exceptional low light capabilities, has enhanced near infrared sensitivity. Econ, working with NVIDIA through the camera partnership, is fine-tuning the TX2 ISP and 290 to achieve high image quality. NVIDIA had put in place a rigorous process through which Econ is getting this solution through, at the end of which we will achieve very high image quality. Look out for this product. This will be launched soon. With this, we come to the end of our presentation. We can move to the Q&A session now.
All right. Thanks, everyone. We'll now move into the live Q&A session, and we've been receiving several of your questions through the chat. So between myself and MKS from Econ, we'll be reading out some of the questions that we've received. Please feel free to continue sending in your questions. We will be saving these and try to follow up afterwards, as well as there'll be a forum posting to continue discussions there as well. One of the things early on the slide with the interfaces, we had gigabit Ethernet, which is supported on Jetson TX2, but we had 10 gigabit bandwidth number there. That's actually 1 gigabit today. MKS, I think there were a lot of questions on your side. Perhaps you can answer some of those.
Sure, James. Thanks. Before getting into the questions, maybe I'll start with an exciting offer. There is a $200 discount coupon being offered on Econ's HexCam solution exclusively for all the participants in this webinar. So please reach out to Econ Systems sales team. The email is available in the last slide of the presentation, and you can get the details. So jumping into the questions, there was one interesting question from Brian from Lockheed Martin. The question was, can cameras across two Jetson boards be synchronized? So the answer is yes. If we can have the same external trigger for both the Jetson boards, yes, it's possible to get this done. James, maybe you want to take a few questions?
Sure. So we got a number of questions about GMSL. So this is a proprietary SerDes interface from Maxim Integrated. GMSL actually stands for Gigabit Serial Multimedia Link. And so this is basically serializing the data to transmit over longer distances. And so Maxim has a standard that's GMSL, as well as Texas Instruments has another SerDes link called FPD link that's very popular as well. So that's what GMSL is. And this is a way to, as I mentioned in the webinar, to extend the distance for CSI. There's a limitation for longer distances with the CSI lanes. So one of these SerDes links is a popular way to increase that distance. I'll hand it back to you, MKS. You seem to have a lot of questions about your cameras.
Sure. Quickly scanning. So there is a question from Sandeep Das at Scania. The question is about, is there source code available so that I can get the 6 frames from all the cameras at any instant of time? So we do share the sample application code for the HexCam, the 6 camera solution. That can be used as a reference and can be utilized for getting the 6 frames at the same instant. There is another question about, is it possible to sync the cameras with other sensors such as LiDARs? Right now we don't support LiDAR sensors. We do not work with LiDAR sensors right now. James, you want to take a few questions?
To touch on the LiDAR, we are working with some of the LiDAR sensor vendors for support on Jetson. But if you have specific questions about interfacing with LiDARs, please feel free to reach out and we can discuss further. MK, it seems like the majority of questions are based on the sync method, so if you can go ahead and answer more of those.
Sure. There was a question on. I'm hoping. Can HexCam be used on TX1 with activating fewer cameras? Was one of the questions. Yes. You can use maximum 6 cameras or any number of cameras less than 6 can be used on TX1. How do you deal with varying levels of exposure? As in, one camera is looking at a bright screen while another is looking at a very dark one. We always sync to the beginning of the exposure. So a simple answer is that it's not just exposure. Say, for example, we can set different gains for each of these cameras. There are other leverages that are available using which we can tweak to address scenarios like different cameras looking at scene with different lighting. So that is one of the advantages of the HexCam. Looking at more questions. Are all your camera applications running on top of Linux? So the answer is yes, we do have applications running on Linux. We also have support for Android. These are the two main platforms in which we have our camera applications running in Econ. So there is a question on, is it possible to customize the position and orientation of the 6 cameras on the 6 camera module? The answer is yes. The hardware that had been shown is more a reference or a used to start with. One can always move around the cameras, position it appropriately to whatever end solution that's being built. So that's possible. So there are questions on price of the what about sync with radar sensors instead of LiDARs? So James, is NVIDIA also looking at radar sensors?
We are taking a look at some of the radar sensors and doing fusion across multiple types of sensors. But there isn't a solution that's readily available today. We would ask that you kind of provide some requirements and details on the application, and we can follow up.
Right. So there was a question on price of the 6 camera. Maybe we can get back to you. It's also available on our online store. Looking at okay, so there is another question about, I don't need 6 cameras, 2 or 3 are enough. Do you have a smaller version of your product? So you don't need a smaller version. This same can be configured to support less than number of cameras. If one is looking for smaller version? Is it in terms of cost, so on and so forth? Maybe we'll need more details. You can reach out to us. There are some specific questions questions on specific sensor support. Somebody is interested. There is interest in support for IMX219 used in Raspberry Pi. Econ does have a service in which if there is an interest for a specific sensor to be interfaced to work with Jetson, we can very well get it done. So please reach out to us and we can take it forward. So there is a question on power consumption on TX2 when GPU is fully used for image processing. James, do you have any information to share in that regard?
Not at this time.
Okay. So sharing our experience, we do not have, may not have actual numbers. So it depends on what the complexity, when somebody says fully used to do image processing, what does fully mean? Is it all the cores kicking in, so on and so forth? But the H.264 and 265 streaming that had been shared, with hardware accelerator being available in Jetson, we use a fraction, certainly not the 100% of the CPU, and the whole of GPU is free. So it's worthwhile to note that there is quite a good amount of power that is available in Jetson, and that's the reason why NVIDIA Jetson had been chosen for some of these complex applications. They're looking into other questions. So there is a question on ways to get a camera frame shared between CPU and GPU. I remembered seeing a documentation available. NVIDIA having shared some documentation on how to efficiently do this, especially in their recent release. There were some support added. Can look into it, or if there is a specific need, please email us and we can answer you, pointing out to where to look for. So there is a question. I am in China. If I buy the product, how long will the delivery take? I think the lead time we've given is minimum is 3 weeks, right? So, but depending on the time and stock, yeah. So we can work on it. There is a question on does the hex cam with IMX290 use DOL HDR? Right now, hex cam is not using IMX290. As mentioned in the presentation, it is using one of on semiconductor sensors. There is a separate product we are working very closely with NVIDIA through the camera partnership program, which will be launched soon. We are targeting to support DOL HDR in that solution too. So that's what our target is. If not in the launching time, at least in the subsequent releases, it will be supported. James, at any time, if you have any questions answered, go ahead and please let me know.
Yeah, I think we're running out of time now. There was a lot of questions being asked, and we appreciate everyone submitting the questions. We'll try to follow up as best we can. And the only thing that I'll mention here, there was a couple questions about Android support, and for Jetson, the Jetson platform, we're a Linux-based platform, and so most of our support will be around Linux.
Just want to thank everybody for coming today, especially to our presenters, to James and MKS. You guys did a great job. As James said, we're going to follow up on the questions will be posted on the forum, so you can look for answers there. And you'll also be emailed a version of the slide deck, and you'll be able to replay the webinar if needed. That email will be hitting your inbox in the next day or so. Thanks again for attending, and we hope to see you at our next webinar.